Hey guys, this is Aaron Carmen from AXE Electronic, back with the next video in our circuit analysis lecture series. So today what we're going to do is I have 5 problems that we're going to work through together, and each of these 5 problems is going to have a capacitor or an inductor in it, and we're going to be looking at how they behave whenever we close or open a switch. So we're looking at their transient behavior for these problems. Now, just as a reminder, I don't have the answers in front of me for these problems, so you're going to be seeing me work these out in real time, and this will hopefully give you some ideas of how to solve these problems, or at least help you identify places where you might get tripped up on these problems. Okay, so without further ado, let's go ahead and get started. For this first one, problem 1, we are going to solve for VC and IC, so the voltage and current for a capacitor. And this is the circuit we're dealing with. So we have a 10 volt source, a switch that is open, a resistor, and a capacitor. So this is a 10 volt source, a 10 ohm resistor, a 1 microfarad capacitor. Now remember, that there is not a messed up M or a messed up U. That's actually the Greek letter mu, which means micro, or times 10 to the power of 6. So this is 1 times 10 to the power of, times 10 to the power of minus 6. So this is 1 times 10 to the power of minus 6 farads, or 1/1,000,000th of a farad. So this switch is going to close at t is equal to 0, and we want to know the voltage across this capacitor and the current through that capacitor. So what I like to do to start these problems off is let's think about what's happening before that switch closes. So let's think about what's happening in the circuit before we close that switch. Well, remember, there's no current flowing, so because it's an open circuit, there's no current flowing, so we know that IC, initial, has to be equal to 0, because there's no way current can flow if it's an open circuit. And then, following that same logic, we can say the initial voltage across the capacitor, if it's not charged, which we're assuming if no current has flowed, then it's not charged, then it'll be 0 volts as well. Okay. So now for this one, this is a problem that we've dealt with before in some of the previous videos. So this is charging up the capacitor. So we know the formula for charging up a capacitor, and that's going to be VC is equal to the supply voltage, Vs, open parentheses, 1 minus e to the negative t over tau. And this is for t greater than or equal to 0. Okay? So now there's a couple of things we know here. We know the supply voltage, Vs. Okay? Now, what is this tau? Okay, so what's that tau? If you remember back in our previous lectures, we said that in this case, tau is equal to just RC. Okay, so we've got just RC here. So let's go ahead and calculate tau, because that's something that's fairly easy to calculate. So if we're calculating tau, that's going to be 10 ohms times 1 microfarad, okay, or just 10 times 10 to the minus 6. Okay, so that's going to be our tau. So I've got my calculator, because for some of these we're going to be needing a calculator, but this is our tau in this case. So now we can plug in all the values we have. So we have VC is equal to Vs, which is 10 volts, open parentheses, 1 minus e to the negative t, and then for tau we're going to put 10 times 10 to the minus 6. Okay. That's for t greater than or equal to 0. And remember, before that switch closes, the voltage across that capacitor is just 0. All right, so let's try and figure out the current now. So the current, once again, we have a formula that we've derived in the previous lectures. So I'm just going to use that. So I'm going to say IC, okay, so the current through that capacitor is going to be equal to Vs divided by R, not open parentheses, e to the negative t over tau. Okay, so we know Vs, we know R, so we have just enough information to solve this. Okay? Oh, we also know tau, so we know everything in this equation. So we can do equals Vs is 10 volts, R is 10 ohms, so that means Vs divided by R is just going to be 1 amp. Okay? That's times e to the negative t. Remember, tau is 10 times 10 to the negative 6, so that's what we'll put here. And that's for t greater than or equal to 0. Okay, so now we've solved for the voltage and the current for this capacitor. So let's try graphing it. So if we try graphing this, I'm going to graph the voltage here for this one, and then I'll make another graph for the current. So let's see what this voltage is going to look like. Well, before t is equal to 0, voltage is just 0. And let me make sure I specify that this is the time axis. So before we flip that switch, the voltage is just equal to 0. Okay, now after we flip that switch, what's going to happen? Well, a capacitor won't change its voltage instantly, so what we're going to see is we're going to see a slow ramp up. Okay, we're going to see a pretty slow ramp up in that capacitor because that resistor is going to prevent current from flowing into it, so that resistor is going to dictate how slow it is. Okay, so we're going to see kind of a ramp up like this, and after a while, it's just going to flatten out. Okay, because after a while, it's pretty much gets to where it's fully charged, and it's just going to get closer and closer to a certain value. Now, what is that value that it's getting closer and closer to as time goes on? Well, after a long time, remember, a capacitor looks just like an open circuit. And if we look at this equation here, let me use the green. If we look at this equation here, we'll see that once t gets really, really big, e to the negative t over tau pretty much just looks like e to a large negative number. Now, e to a large negative number is pretty close to 0. It's almost 0. So if we have 10 volts times 1 minus almost 0, that's really just about 10 volts. So that's what we're approaching here. It's 10 volts. And then initially, we started off at 0 volts. Okay, so now we've graphed the voltage. Let's try graphing the current. Okay, this is T, and then I'm graphing current here, so IC. So now, once again, before T is equal to 0, we just have 0 current because it's an open circuit, so no current is going to be flowing. Now, as soon as we close that switch, there's going to be a big spike of current because that capacitor is going to be charging up very quickly. Okay, so that spike of current is shown just here. That's the maximum value. So this is going to immediately jump up to 1 amp, okay, and then it's going to sort of taper off like this, right? Because after a while, the capacitor is going to be like an open circuit and not going to let any current flow through at all. So after a long time, it's going to get close to 0 volts. So I'll make a little dashed line here, or sorry, not 0 volts, 0 amps, just to make sure we know that it's going to approach 0 amps of current. Now, if you were asked what's this initial value here, then you can very easily say it's just this value, 1 amp. So this is 1 amp here. So it reaches a peak of 1 amp and then starts decaying. Right? And this makes sense because as a capacitor gets more and more charged, okay, the potential difference across a resistor is going to get smaller and smaller and smaller, and eventually that capacitor will be fully charged and won't let any more current flow through. Okay? So we finished number 1. So this one was pretty easy, but we made sure we did everything carefully and we solved everything for this first one. Let's move on to number 2. So in number 2, we're dealing with a resistor and an inductor. So this is going to be a 6-volt source. We're going to have a switch that is open. It's going to close at t is equal to 0. Then we have a 2 millihenry inductor. Okay. And over here we have a resistor. And this resistance is 3 ohms. Now, what are we solving for here? Well, I haven't told you yet, so I'm going to tell you. We are solving for VR and IR. So we're solving for the voltage and the current of that resistor. So let me mark that in the schematic. We're solving for VR and IR. So how can we go about doing this? Well, we have a formula for the current through an inductor that we know. And if we know the current through the inductor after that switch is closed, then we can just use Ohm's law to get the voltage across the resistor. Okay? And once again, if we know the current through the inductor, that's going to be equal to the current through the resistor because there's no other branch for this current to flow. Okay, so what I'm going to write here, just to make a note to myself, IL is equal to IR. Okay, and then I'm also going to make another note. I'm going to say VR, let me use the scripted V, so VR is equal to IR times R. That's just Ohm's law. Okay, so we know this to be true. Now, before we start getting into the math, let's think about what are the initial values for voltage and current. Well, for current, that's easy. We have an open circuit, so there can't be any current flow at all. So the initial current is going to be 0 amps. And then, once again, what's our initial voltage? Well, we know Ohm's law relates relates current and voltage relative to resistance. So we know the resistance, we know the current is 0 amps, so that means we know that the voltage is 0 volts. Okay? So now let's use the formula that we have for the current through an inductor to figure out what is the current through the inductor and the resistor. So from a previous video, that formula is IL equals the steady state current, which is going to be Vs divided by R, times 1 minus e to the negative t over tau for t greater than or equal to 0. So what is tau in this case? Well, previously tau was RC, so maybe for this one it's RL, but that's not correct. This is one of the things that you have to remember. Tau for an inductor and a resistor is not RL, it's L over R. Okay, so this is something you have to remember. For an inductor and a resistor, it's L over R. For an inductor, for a capacitor and a resistor, it's going to be RC. Okay, so our tau is L over R. Let's go ahead and calculate this. So this is 2 millihenries divided by this 3 ohm resistor. Okay, so this is 2e minus 3 divided by 3, and that's going to be, let's see, this is going to be equal to 667 times 10 to the minus 6. Okay, so this is the time constant that we have for this circuit. So we know Vs, we know R, we know tau. We have enough information to solve for the current through this inductor. Let's do IL is equal to Vs, which is 6 volts, divided by R, which is 3 ohms. This will be 2 amps, times 1 minus e to the negative t over tau, which is 667 times 10 to the minus 6. Okay? And that's for t greater than or equal to 0. So now we have the current through the inductor. Well, current through the resistor, remember, is the same thing as the current through the inductor. Okay, so now we know the current through the resistor. Now how can we get the voltage through that resistor? Well, remember, Ohm's law just says V is equal to I times R. So VR is equal to IR times R. So if we do that in this case, that means that the voltage across that resistor is just going to be 6 volts, 1 minus e to the negative t divided by 667 times 10 to the minus 6. Okay, for t greater than or equal to 0. Okay, so now we know the voltage and the current for that resistor. Now we can try graphing these. So let's graph the voltage. I'll start off with the voltage again. So this is T, and I'm plotting voltage across that resistor. So initially, remember, it's 0. We initially have 0 volts across that resistor. Now, if we look at this equation, you can see that this is the same equation as that slow ramp up, right? So whenever you have that 1 minus e, that's going to be the slow ramp up. If it's just e to the negative something, then that's going to be a spike, then come down. Or that the e to the negative something means it's exponentially decreasing. 1 minus e to the negative something is going to be that ramp up that we've seen before. So we know that the voltage is going to look something like this, right? Where it approaches a value after a certain amount of time, and we might be asked, well, what is that value? After a long time, what is the voltage across that resistor? Well, remember, inductors are like short circuits after a long time. So we can tell from this circuit, if the inductor is just a short, the voltage across that resistor is just going to be 6 volts. Okay, and again, from this equation here, we can see that after a long amount of time has passed, once again, the voltage is going to be 6 volts. So we know that the steady state voltage across that resistor is 6 volts. Now what's the initial value? Well, again, from the equation and from what we know about inductors, we know they're going to resist current. So initially that current's not going to that inductor's not going to let any current flow. And if no current's flowing, there can't be any voltage across that resistor. So we're going to start off at 0 volts and then ramp up and approach 6 volts. Now what about the current? Well, the current, remember, IR, follows a similar pattern, okay? The only thing that changes is that instead of having a 6 volts as our, for this value, we have 2 amps here. Okay, so we're going to be following a similar path where we start off at 0 and then we have that slow ramp up. Now what's it going to be ramping up to? Well, like we said before, that's just 2 amps. Okay, and we can see that from the equation, or we can see that from the circuit if we think of the inductor as just a short. Okay? And the initial value here is going to be 0 amps, right? Because initially that inductor is not going to let any current flow at all. All right, so this is number 2. This one was a little bit more confusing because we were dealing with the resistor and we had to think a little bit, but still this one isn't too bad. Okay? So now let's move on to number 3. So number 3. For number 3, let me scroll down in my notes so I can see the problem statement. Number 3, we have 15 volts, 15 volt source, a switch that is normally closed, or that was closed for a long time before, and will open at t equals 0. And then we have one capacitor, another capacitor in parallel, and then a 7 ohm resistor over here. This is 1 millifarad, 6 millifarads, and 7 ohms. And we want to solve, let's see, we're going to solve, once again, we're going to solve VR and IR. So we're going to be solving for the voltage and the current for this resistor. So this one, we've kind of seen something that looks like this before, right? Because we looked at what happens when capacitors discharge in the capacitors video, but we haven't looked at one like this where we have 2 different capacitors. So how are we going to handle this? Okay, well, hopefully you watched my last video, which talked about how we can combine capacitors and inductors. So what we can do here is we can identify that, well, we have these 2 capacitors in parallel. There should be a way to combine them into an equivalent capacitance. Okay, so let's rewrite this circuit. This is going to be 15 volts again, with a switch that was closed and is opening at t is equal to 0. So instead of having those 2 capacitors, we're just going to have an equivalent capacitance and this resistor. Okay, so this is 7 ohm resistor. What is this equivalent capacitance? Well, we have 2 capacitors in parallel, so maybe we should use the equation for parallel resistors. I mean, maybe capacitors work the same way. Well, like I said, if you had watched my previous video, you would know that that actually is not the case. So capacitors in parallel, their capacitances actually add. Okay, and if that doesn't make sense to you, like I said, please feel free to go back and watch that previous video. I explain it in a whole lot more detail there. But for now, all we need to know is that these 2 capacitors are going to add into an equivalent capacitance. So if we add these 2 capacitors, 1 millifarad plus 6 millifarad is going to be 7 millifarad. So now we just have a capacitor and a resistor, and this is just a capacitor discharge problem. Okay, so we've seen something like this before. So the new thing that we've seen in this problem is how can we combine those capacitors into an equivalent capacitance. So now that we have this simplified circuit, let's think about what's going to happen. Okay, what happens before we open that switch, and what do we think is going to happen afterward? Well, before we open that switch, we're going to assume it's been connected for a long time. That capacitor is probably fully charged by this point. And if that capacitor is fully charged, that's acting like just an open circuit. So we're expecting the voltage across the resistor to initially be, well, just the supply voltage, so 15 volts. And same thing, we're expecting the initial current to be related by Ohm's law. So 15 volts divided by 7 ohms. And I'm going to need to whip out the calculator for this one because I can't do that math in my head. 15 divided by 7 is going to give us 2.14 amps. Okay, so this is the initial voltage and current through that, or voltage and current for that resistor. So now, what's going to happen whenever we open that switch? So whenever we open that switch, that capacitor is going to be fully charged, right? So it's going to start dumping some of its charge into the resistor, okay, to keep its potential up, because the capacitor doesn't like changing its potential very quickly, so it's going to try and keep its potential constant, okay? So it's going to supply that potential to the resistor, all right? So what's going to happen is that whenever we open that switch, that capacitor is going to keep a current flowing through the resistor. And before, whenever we looked at this problem in the capacitors video, we derived the expression for the voltage across the capacitor in this case. So we said the voltage across the capacitor is equal to the initial voltage, okay, which in this case is 15 volts, or just the supply voltage, times e to the negative t over tau. Okay, so this is actually equal to the voltage across the resistor, right? Because all that potential has to be dissipated somewhere because of Kirchhoff's loop rule, or Kirchhoff's voltage law. Okay, so the only place that voltage can be dissipated is across that resistor. So that's how we know that VC is equal to VR. So let's go ahead and try and find what VC is. Well, we know that the initial value is 15 volts. And then we have e to the negative t. Well, what's tau in this case? So tau is just still RC. okay, because nothing has changed. It's still a resistor and a capacitor, so tau is going to be RC. So in this case, that's going to be 7 ohms times 7 millifarads. And if we work that out, that's going to be 0.049. So that's our tau. So we can put that over here. And this is going to be for t greater than or equal to 0. So this is the voltage across that capacitor, which is the same as the voltage across that resistor. So now we found the voltage across the resistor. Now, how can we get the current through that resistor? Okay, well, think about it. Current through a resistor is the voltage divided by the resistance. And we know the voltage divided by the resistor, so all we have to do is divide that by the resistance. So what this is going to give us is it's going to give us 2.14 e to the negative t over 0.049. All right? So we know the current, we know the voltage. Let's go ahead and graph these. So I'll start off graphing the current again, or not the current, excuse me, the voltage. So let's start off the voltage for that resistor. So the voltage before we open that switch is just 15 volts, right? Because we set up here that the initial voltage across that resistor is a constant 15 volts. Okay, so we know that this is originally 15 volts before we open that switch. Now, what's going to happen whenever we open it is that we start having this decay from 15 volts, because this is what that looks like. This equation looks like a decay. So we're going to have a high voltage, we're going to have whatever we started off with, and then it's going to decay. So we're expecting this to look something like this. Okay? So what does this start off at? Well, it's going to start off at the same 15 volts. And then what's it going to approach as time passes on? Well, that capacitor can't supply charge forever, so it's going to approach just 0 volts. So now let's graph the current. So if we graph the current, this is T, and then this is IR. The current is going to look very similar. So we start off, remember, with that 2.14 amps that we said we had above. Okay? And now if we look at this equation, we can see that we have that same decay from 2.14 amps. So we're going to decay like this. We're approaching 0 amps and starting off at 2.14 amps. Okay? So this is what that voltage and current for that resistor is going to look like. We're going to start off at a certain value, okay, and then once we open that switch, the capacitor is going to try and keep supplying that resistor with voltage. Okay, but as it supplies it with more current, it's going to reduce its potential. So that's why we're seeing that decay in the voltage and current. Okay? So this one, like we said, the biggest trick for this one is knowing how to combine those two capacitors. That way we can make this a simpler problem. Okay? So this one, again, wasn't too bad. All you need to know was know the tricks to combine the capacitors. So let's move on now to number 4. So number 4, we've got solve for VL and solve for VL and VR. Okay. So you can see this one, typically we're solving for voltage and current. Now we're only caring about 2 different voltages. So let's see. So we've got a 20 volt source. And then two different switches. Okay, let me get this drawn. A resistor and an inductor in series. And then over here, we're going to have just a resistor. So initially that switch is closed here, and it's going to flip at t is equal to 0. All right, and we're trying to solve for this voltage across the inductor and this voltage across the resistor. Okay, so this one I can already tell is going to be a little more complex just because of the arrangement and because, I have a little more experience with this. So let's analyze this and see what's going on. So let's start off with a very top-down view and just talk in a broad sense about what's going to happen in this circuit. So initially we have 20 volts connected with this inductor and a resistor. Let me give you all the values first before I start talking. So this inductor is going to be 5 millihenries. The resistor is 100 ohms. And this is a 100 ohm resistor over here. So initially we have 20 volts going into that 5 millihenry and 100 ohm resistor. So what is this going to be doing after a long amount of time? Because we're assuming that switch has been connected for a long time. Well, remember, after a long time, inductors start to look like a short circuit. So really, it's just going to be that 20 volts being dropped completely across that 100 ohm resistor. Okay? So we have 100 volts being dropped across that we have 20 volts being dropped across a 100 ohm resistor. We can calculate the current through that inductor and through that resistor. So that's just going to be 20 volts divided by 100 ohms, which is just, let me make sure I write this here. So I'm going to do IL initial, okay, because we're talking about the current through the inductor, is initially 0.2 amps. Okay? So that's the initial current through that inductor. Now what's going to happen is, whenever we flip that switch, okay, whenever we flip that switch to the other side, that inductor isn't going to want to stop supplying current, because remember, inductors don't like having their current changed. Okay? They like to keep a constant current if they can. Okay, so they're going to resist a change in current. That means that inductor is going to start supplying current to the rest of the circuit. Okay, so that inductor is going to supply that same current to a 100 ohm resistor as well as the other 100 ohm resistor in order to close that circuit. So that's the only way that that inductor is going to be able to keep its current flowing. Okay, so in this polarity, okay, we know that the inductor is going to try supplying current downward for the inductor. And in order to do that, it actually has to have a negative voltage, okay? Because of the way we drew this, the voltage is actually going to be negative, okay? Or if we draw it this way, it's going to have a positive voltage in that direction because it's going to try and supply current. Okay, so you can think of this inductor as now sort of acting like a source, okay? So it's acting like a source that is supplying current to the rest of the circuit, okay? Because initially, it would have a voltage drop, but then that would sort of die out by the time it starts acting like a short circuit. But in order to keep that current going, we need to have a voltage pushing that current. So that inductor will supply that voltage. Okay? Now, using this information, we can derive the expression for the current through that inductor. Right? Because we know that inductors, it's typically easier to work with their currents. Okay, so let's do that. Okay, so let's start by working that out. So we're going to say IL. IL is going to be equal to its initial value of current, which was Vs divided by 100 ohms here, because the supply was initially having to supply current only to that 100 ohm resistor. Okay, so it's going to be Vs divided by 100 ohms because that's the initial amount of current, which we said was 0.2 amps. Okay. And then from there, it's going to decay downward because that inductor can't supply current forever. Okay. So it's going to decay downward at a rate of e to the negative t over tau. Okay. So this one is actually a little bit interesting, okay, because you might be thinking, well, you know, tau we said is L over R, but which R do we use in this case? Okay. Well, let's think about this for a second. So whenever we flip that switch, all we have is an inductor, a resistor, and a resistor. Okay, and those two resistors are in series. So all the inductor can see, you know, if we're in the shoes of the inductor, all we're going to see is an equivalent resistance that's equal to 100 ohms plus 100 ohms. Okay, so whenever we're calculating tau, it's going to be L divided by the resistance that the inductor sees, which in this case is going to be 5 millihenries divided by 200 ohms, right? Because it's seeing those two resistors in series. So this is going to be tau, all right? So this is what tau is. Let me go ahead and calculate this for you. So it's 5e minus 3 divided by 200 ohms. Okay, so this is 25 times 10 to the minus 6. So that's our value of tau. And the tricky thing is that you can't just use L divided by R as in 5 millihenries divided by 100 ohms, because you have to think, well, for this inductor discharging, whenever it's discharging, this is seeing a resistance of 200 ohms actually. So this is one of the connections that you have to make, okay, to get this problem correct. Okay? So now we can just derive the rest of this current. So we have IL is equal to Vs divided by 100 ohms, which is just 0.2 amps. Because remember, this is the current that the inductor initially had, and it's not going to want to change it. So this is what we're going to start off at, 0.2 amps. And then we'll have, let me get that all erased, e to the negative t over 25 times 10 to the minus 6. Okay? And this is only for t greater than or equal to 0. Okay? So this is the current through that inductor. Now how can we calculate the voltage for that inductor? Well, there's a couple of different ways, and personally, I really don't want to have to think about it too very much. So instead of doing all this, what I'm actually going to do is I'm going to go a little bit longer of a route, but I think it might be a little bit simpler to understand. Okay? So now we know that this inductor is supplying this amount of current. Okay? Now, if it's supplying this amount of current, that current is going through this first 100 ohm resistor and that second 100 ohm resistor. Okay? So that current, so that current is going through both of those resistors, and that means that the inductor has to supply a voltage for both of those resistors. It has to be able to supply a voltage to push the current through those two resistors. So that's how we're going to calculate the voltage for this inductor. So we're going to say voltage across this inductor is going to be equal to the current through the inductor, because that's the current through these resistors, times R1 plus R2. Okay. Now, the reason we're doing this is because let me rewrite this a little bit. So let me call this one R1 and this other one R2, just to make sure we're making sense of this. The voltage across the inductor has to be equal to the voltage across the first resistor, so VR1, plus VR2. And this is just Kirchhoff's voltage law. Okay, this is Kirchhoff's loop rule. And all I did was substitute Ohm's law in here, so we get VL is equal to IL times these two resistors, R1 plus R2. Okay, so if we do this, we can say VL is equal to, let me just go ahead and plug this in. So R1 plus R2 is 200 ohms times 0.2 amps. That'll give us 40 volts. So 40, and then the rest of this current equation, which is e to the negative t over 25 times 10 to the minus 6. Okay, so this is the voltage across that inductor. Okay, but there is one thing we need to sort of catch, because remember, whenever I first gave you this problem, I wrote VL like this, plus and minus. Okay, but in order to push the current through this circuit, this voltage, the way I wrote it here, has to actually be negative. Okay, so it's going to be negative 40 volts because of the way we're measuring it. Now, if instead of having it written this way, if instead of writing it like this, I wrote it with the signs flipped, so negative and positive, then you would say that that voltage is positive 40 volts. But because of the way I wrote it, which was positive and negative, this has to be negative, okay? Because the inductor is supplying voltage downward, so there's going to be a voltage rise from the top to the bottom, okay? And a voltage rise is pretty much the same thing as a negative voltage drop. So that's why we have this negative here, okay? So now we know the voltage across that inductor. Let's calculate the voltage across that resistor, and then we'll be done with this problem and we can graph it. Okay, so the voltage across the resistor. Now voltage across the resistor is easy. It's just the current through the resistor times the resistance. Okay? So once again, we will do IL, because IL and IR are the same thing, times 100 ohms. Because we're just concerned about that one resistor, which only has a resistance of 100 ohms. And if we plug this in, we will get that that voltage is 20 e to the negative t over 25 times 10 to the minus 6. But now we have to check ourselves again, because remember, I wrote this with the positive sign up and the negative sign down. But if we have a current going in this direction, okay, if we have a current through that resistor going from bottom to top, that means there is going to be a drop from bottom to top. Okay, so initially, if we had it written this way, then we would be expecting a positive drop, okay, or that positive voltage. But because we wrote it backwards, okay, so because it's negative and positive, we're actually expecting a voltage rise in this case, because we're saying if we go from here down to the bottom, that voltage is actually going to increase. Okay, so this is actually, once again, a negative value. And all that has to do is with the way that the plus and minus were written. Okay, so that's something important to keep in mind, is that the polarity of voltage does matter. Okay, so if you have the backwards signs, then that's going to cause you to get a backwards answer or a negative answer. So let's graph these two. So if we graph voltage for the inductor, so this is T, and I'm graphing VL. VL up here, remember this is negative 40 for T greater than or equal to 0. Before that, the voltage across the inductor was just 0. Okay, and then it dropped to a negative value. And as time went on, it started approaching 0. Okay, so as time went on, it approached 0 volts. Now, what was this peak here? The right answer for this is negative 40 volts. Okay, because once again, like we said, that negative voltage means that it's supplying that voltage. Okay, so this is the voltage across the inductor. Let's look at the voltage across the resistor. So let me use the blue here. VR. VR is going to look very similar, okay, because initially it doesn't have any voltage drop across it because it's not connected to the circuit. Okay? But then once we flip that switch, remember we said it's going to drop to negative 20 and then have that same decay. Okay? So it's going to drop to negative 20 volts here and then decay to 0 volts. So this one was definitely a little bit more challenging. You know, we had to think quite a bit. We had to work some things out. But all of these problems like this, you just have to work them out one step at a time. Okay, so just make sure you're double checking yourself on everything you're doing, making sure everything makes sense. And you know, it doesn't ever hurt to go back and make sure that Kirchhoff's voltage law is satisfied, because Kirchhoff's voltage law is the best way to make sure that you're doing your signs on these correctly. All right, because if you didn't have these negative values, then what you would end up with is Kirchhoff's voltage law not being satisfied. Alrighty, so the last thing we're going to do is we are going to work out a little bit simpler of a problem. Okay, so this one, you know, it's a little bit simpler, but it's still something that we haven't practiced before yet. So let's go ahead and try this one out. So this one, we're going to solve for VR and IR. Okay, so we're back to voltage and current for a resistor. So this one, we're going to have a 12-volt source, a switch that was open, and is going to close at t is equal to 0. And then we're going to have two inductors this time, and then a resistor. Okay, and this resistor is 10 ohms. This is a 8 millihenry inductor, and this is a 12 millihenry inductor. So this looks sort of close to one that we did in the inductor video, you know, an example we did in the inductor video, but you know, it's still not quite what we want because we have those two inductors there and we're not 100% sure how to handle that and we don't want to have to rederive everything. Well, go back, look at the previous video and see what we can do to inductors in series. Okay, so the answer is what we can do is we can combine these into an equivalent inductance. Okay, so we'll have this 12 volts, the switch, and then this equivalent inductance and a resistor. And that didn't look too good, so let me go ahead and fix that. Okay, and this closes at t is equal to 0. Now, what is this equivalent inductance? Well, inductors in series, okay, are inductors in series going to add, or are we going to use the formula for parallel resistors? Okay, so inductors in series, what are they going to do? Well, if you watched the previous video, you should know that inductors in series are going to add together. Okay, so inductors in series add up, their total inductance is going to increase. Okay, so that's what we can do here. So here, if we add these two inductances, what we're going to get is 20 millihenries here. And then here we have just a 10 ohm resistor, and we're concerned with the voltage and current across this resistor. Okay, so this is still a relatively simple problem. Okay, so now that we've transformed it into something we know how to work with, we can use the formulas from before. So let's think for the voltage and current across this resistor, what are they initially? So before we close that switch. Well, we know the current is going to be equal to 0 because it's an open circuit. And if the current is 0, then Ohm's law says the voltage across that resistor has to be 0 as well. So that's going to be 0 volts. All right, so now let's figure out what is the current through this resistor first. Because like I've said, we're dealing with inductors, and inductors, it's typically easier to find out their current than it is their voltage. Okay? So let's figure out the current through this resistor. So the current through the resistor is going to be equal to the current through the inductor because there's no other branch, right? So because of this, we can use the formula for the current through an inductor, which is just Vs divided by R, okay? And then 1 minus e to the negative t over tau. This is for t greater than or equal to 0. So we know everything here. Let's just review one last time. Tau for an inductor and resistor is just going to be L divided by R. So let's calculate this. That's 20 e minus 3 divided by the resistor, which is 10 ohms. So that's just 0.002. So that's the value of tau. So now we can plug this in here. IR is just going to be equal to Vs, which is 12 volts, divided by 10 ohms, and then 1 minus e to the negative t over 0.002 for t greater than or equal to 0. Alrighty, so we can just take this one step further and solve it as 1.2 amps e to the negative, 1 minus e to the negative t over 0.002. Gotta make sure you keep track of those zeros. So then t greater than or equal to 0. So now we have IR. So how do we get the voltage across that resistor if we know the current? Well, you should be saying, we have Ohm's law. Ohm's law is pretty simple, so we just do VR is equal to IR times R. Okay, and once you manipulate that, you'll find that this is just equal to 12 volts, 1 minus e to the negative t, divided by 0.002 for t greater than or equal to 0. So last thing we're going to do is we're just going to go ahead and graph this. So I'm going to start, like I always do, with the voltage across this resistor. Now initially, it has 0 volts because it's an open circuit. Now once we close that switch, the current is going to start ramping up, so the voltage is going to start ramping up. And it'll ramp up like this, and it'll approach a certain value, and it'll sort of just stay there. It's going to asymptotically approach that value. Now what's that value? That value is just the supply voltage. So we're just going to put, we're just going to put 12 volts here. And the initial value is 0 volts. So now let's do the same thing for the current. So the current through that resistor, again, initially is just 0 because it's an open circuit. And then what's going to happen after that? Well, after we close that switch, remember the inductor is going to resist that current flow, but it is going to let it ramp up. Okay, after a long amount of time, it's going to let it ramp up. Or after a long amount of time, it's going to act like it's not even there. Okay, so we're going to see this ramping up. Now, what is this steady state value? This steady state value is just Vs divided by R, which is 1.2 amps. And we could tell that from the equation as well. And then here, what is it initially? Well, it's initially 0 amps because that inductor is going to resist any change in the current. Okay, so I hope you enjoyed this. If you have any questions, please feel free to leave them in the comments below. If you work some of these problems out and you think I did something wrong, please definitely let me know because, like I said, I don't have the answers for these. Okay, and it's been a while since I've done any sort of real serious circuit analysis like this. So there's definitely a chance I did something wrong. And if you can catch that, then that just shows that you know as much about this as you should at this point. Okay, so guys, like I said, I hope you did enjoy this. Please feel free to leave me a comment. If you liked this video, give me a thumbs up and subscribe for more content like this. Otherwise, I'm Aaron Carmen, and thank you for watching.